Welcome to our final lecture that'll start with the binomial random variable, and after this lecture we're going to be experts across the discrete space of random variables. So buckle up, this one's going to be exciting. So recall again, you really want to get this one in our head, the binomial random variable. By this time we probably memorized its moment generating function, its probability mass function, its expectation, its variance. Let's recall from our last lecture. We learned about modeling events that aren't quite binomial with the binomial random variable. Those events were the hypergeometric distribution, the multinomial distribution. We also used the binomial to model the amount of rain occurring over a 3-day, 1 week, 1 month, and 1 year interval in Central Park. What did we see? We saw that doesn't work perfectly for the multinomial, obviously, especially at the edge cases. Doesn't work perfectly for the hypergeometric, but we also saw some issues with our modeling of real data are that it seems to underestimate the variance associated with real data, and also that as n gets really large, it's not that easy to calculate. So what we're going to do now is we're going to sort of attack that problem. It's what do we do when the binomial random variable gets really big? So for that, we're going to consider a test case where imagine that we have a sample that includes 10 billion trials, right? So that's a very big number. And we also know that the approximate fraction of successes that are in that world of 10 billion are approximately 1 billion. The probability, of course, is 1 over 1 billion. So we know the expectation. The probability of success is 1 over 1 billion, and we're going to do 10 billion trials. We know the expectation is that we're going to see 10 successes. But how do we calculate the probability of 10 successes? We know it's the peak of the distribution, but we don't know its probability. And when we look at the mass function, it looks daunting, right? So instead of doing this explicit problem, let's examine what happens to a binomial random variable as the number of trials go to infinity. To do that, we're going to take a trip, of course, back to whiteboard. So for the first step, we're going to rewrite the distribution function and set a new variable lambda as equal to np, which of course means p equals lambda over n. Okay, so for the second step, because we're taking the limit as n goes to infinity, we can factor out terms that don't include n. So we factor out lambda to the x over x factorial. And we're going to rewrite it as 3 separate terms. And initially, we're going to focus on this first term. So in the third step, we notice that there are n terms in the numerator and n minus x terms in the denominator, which will cancel, leaving us x terms on top. So we have n times n minus 1 all the way until n minus x plus 1. And of course, because we also have a 1 over n to the x, we can put an n raised to the x power on the bottom. This gives us n terms on top and n terms on the bottom. And we know that n over n times n minus 1 over n all the way until n minus some constant plus 1 over n. As n goes to infinity, we'll limit to 1. And now we focus on the second box, and we take the limit as n goes to infinity of 1 minus lambda over n raised to the nth power. And here we take advantage of the fact that 1 minus 1 over n raised to the nth power is just the exponential. So we just make a substitution, and we set y equals negative n over lambda, giving us 1 over 1 plus y raised to the y times negative lambda, which of course equals e to the negative lambda. So finally, we notice that because our last term, 1 minus lambda over n to the negative x, just goes to 1 as n goes to infinity, the only surviving term is our e to the negative lambda, so we combine it with what we pulled out previously, which was lambda to the x over x factorial. And we now have determined that the limit of the distribution function of x as n goes to infinity is lambda to the x e to the negative lambda over x factorial. So that's pretty cool. So as n goes to infinity, the limit distribution for the binomial random variable is the Poissons distribution. And the Poissons distribution has only a single parameter, lambda. It's pretty cool. Lambda is actually equal to both the variance and the mean, which solves one of our problems, which was that we see that consistently that the mean is much bigger than the variance. Well, in this case, the mean and the variance are the same, right? So in the binomial, of course, the mean is always bigger. In the Poisson, the mean and the variance are equal. And of course, we can talk about a classic example for the Poisson, which was first used to model how many soldiers were kicked by horses in a cavalry, in the Prussian cavalry, right? So of course, there are more real-world ways to use the Poisson distribution. I think the example of the patients entering the ER is a really good example for us to understand how we use the Poisson distribution to model real data, right? So imagine we have data about every amount of patients that entered the ER for every hour. And we don't want to use the binomial random variable because we see that in this data, the mean and the variance look equal, right? So that's a hint that maybe we should be using a Poisson distribution. But we say, well, we only have data from 12 hours and we have the amount of patients per hour. We can't use a Poisson to describe that because 12 hours is definitely not close to an infinite number. And the Poisson is approximate only when it's binomial and going to infinity. But remember, when you have time intervals is when you're going to see the Poisson pop up a lot because we can make n be whatever we want. Right? So for example, if we're doing 1 hour, we can say that n, each trial is actually 1 second. Right? So now we have 3,600 intervals, right? So every second, there's a chance a patient walks in through that door, and the probability of that's pretty small, right? So let's say, for example, if we're saying on average 5 per hour, we say, well, the probability is so small that NP over the course of an hour is 5. So now we've justified using a Poisson because as long as we think that we can separate our trials into smaller trials with equal probability, a Poisson is justified. Now you can't always do that. So for example, if you are looking at a binomial random variable that's been used to model, for example, shooting of free throws into a basket, shooting 10 shots, the amount that you make out of 10 shots, that can't be modeled with a Poisson because you can't separate free throws into half free throws. Right? It's not that you can shoot a half free throw as a probability of making a half free throw. It's only 10 shots. So when you can't separate your interval to cause n to be infinite, the Poisson is not appropriate. But when you can, it is appropriate. Or if it's not, so you'll see the Poisson popping up across intervals, right, across time, or when the space that you're trying to model is actually pretty close to infinite. So for example, the amount of molecules inside of a cell, the amount of the meteorites that could hit any space, any place on Earth at any given time. So you see that the Poisson distribution has a lot of really nice properties. This mean and variance being the same is really, really useful. But if we have the binomial random variable, where the mean is always greater than the variance, the Poisson, where they're always equal, you can imagine there might be a desire for a random variable that's analogous to these two, but has variance always greater than mean. And we do have that. We have the negative binomial distributed random variable. This is a confusing one because there's different ways to parameterize this distribution. So the one that we're going to use is a parameterization that has R and P as the parameters. So P is the same as the binomial, right? But R, instead of being the number of trials, R is the number of failures. So what that means is if I'm asking probability of seeing 50 successes in 100 tosses of a coin, that we could use a binomial there, right? And if the coin is fair, the expectation would be 50. So probability would be highest there. For the negative binomial, we wouldn't ask that. We would ask, what's the probability of seeing 50 successes before I see 50 failures? So here we can infer n by taking the amount of successes and failures, right? So we add those up and we get n, right? So we can have, so n isn't fixed, but n sort of depends on what happens, whereas in the binomial, n is fixed, and we're asking about k, which then determines the amount of failures. Here we fix the amount of failures, we ask about K, which determines the total events, which is N, right? So this probability distribution function is really popular. It's also used for a lot of gambling type scenarios where you talk about, sort of going on a streak, because of course here you can have many successes despite very few failures if you get lucky, right? So because of that, because there's many ways to have successes with or without failures, what you'll see is that this distribution has a much larger variance than the binomial. So we're gonna look at that right now. The distribution function, and what we're seeing here is, okay, in the case of the binomial, we're saying, what's the probability distribution function look like across K for 100 trials, where success probability per trial is 0.5. So of course we know that the mean is gonna be NP. So the mean is gonna be on average 50 successes. And then what we look at for the negative binomial is we say, what does K look like? What's the probability across different values for K when the probability of the success on a single trial is 0.5, and we have 50 failures. So after 50 failures, how many successes do we have? What's the probability for different values of success? So the first thing that should just be obvious is, for the binomial, K can only be up to 100, right? So the support is constrained. If you have 100 trials, you only have 100 successes. Whereas for the negative binomial, it's not. So how many successes can you have after 50 failures? Well, you could start off with 300 successes, and then have 50 failures. Again, for this probability, that's unlikely, but possible. So the negative binomial support goes from 0 to infinity, right? So that spreads out the variance. Yeah, so because N isn't fixed, right, we can say, okay, well, after 50 failures, there's many things that could have happened, right? We could have had 0 successes, 1 success, 2 success, all the way up to almost infinite amount of successes that could have happened in the space of 50 failures. So while it still has the same mean, right, which is also intuitive, right, how many successes would I imagine would happen after 50 failures, given that they're equal probability? Well, the same, of course, right, 50. So they're the same mean, but the variance is very spread out on the negative binomial distribution. And in fact, what we can show is that the negative binomial distribution always has variance greater than mean. So what we have here, between the Poisson, the negative binomial, and the binomial, we have 3 random variables, one with mean less than variance, one with mean equal to variance, and one with variance greater than mean. Because there's been a lot of interest in this relationship between mean and variance of these discrete random variables, we can actually summarize all 3 of them into something called the generalized Poisson. So because the Poisson has equal mean and variance with a single parameter, we can say, okay, the basic, the most simplest Poisson is going to be the Poisson with the dispersion parameter of 1, right? So that's just the Poisson. Then we have this other parameter that we can change to change the amount of variance relative to the mean. So that way we can start with a Poisson and get something that looks more like a binomial, right? We would say has deflationary variance, or it looks more like a negative binomial. In fact, we can also show that the negative binomial is just a special case of the generalized Poisson distribution. So we can sort of wrap up all 3 of those into sort of one idea of the discrete random variables that tell you something about the amount of successes over some amount of either trials, or you can change the stopping condition to failures, of course, in the case of the negative binomial, and allow us to model different phenomenon that has different mean variance relationship. Of course, all 3 of those random variables all are modeling success, where success probability is unchanged. You can see how we have this sort of desire to encapsulate things in a single distribution, like we do with the generalized Poisson. What if we could actually encapsulate all of these into one distribution? So all of our discrete random variables into one distribution that's going to tell us something about probabilities of successes and failures on some interval. We do this by introducing a random variable that may easily overfit our data, right? And what that's called is the beta binomial distributed random variable. And so that is, the way we think of that is, it's a binomial random variable. However, the probability of success on each trial is each time drawn randomly from a beta distribution. right? So we have a probability distribution, the beta, that we draw a p from, and then we run a trial. What's interesting about the beta distribution is that actually gives us flexibility to generalize this distribution into any of those other distributions that we want. So for example, if we set our parameters for our beta binomial, if we set them to be positive integer values, like say 30 and 70, then the beta binomial distribution will model the probability of seeing, for example, if you have a bag of marbles where you have, say, 30 red marbles and 70 black marbles, then probability of k equals 20 will be the probability of seeing 20 draws of red marbles under the condition that each time you draw a marble from the bag, you put back 2 of the same kind. So it's a riff on the hypergeometric, right? And for non-integer values, you can actually use the beta binomial to approximate the negative binomial, the Poisson, basically all of our distributions. And of course, when alpha and beta are both equal to 1, the beta binomial is just the discrete uniform, right? So it's the numbers of successes, on some interval, which in the beta binomial is going to be 0 to n, they're all going to have equal probability of alpha and beta equal 1. So with that, we've actually wrapped up. So with the beta binomial, we've encapsulated all of our discrete random variables, all the ones we're going to talk about in this class, and we've actually put like a nice cap on this whole section of class. With the beta binomial in mind, we can add that to our chart of random variables. And again, we can make our quadrant of random variables, right, which is our categorical, multinomial, Bernoulli, and binomial, which we know all have an intimate relationship with each other. We can call that sort of our quadrant. And then we can also put a triangle, so to speak, around our binomial, our Poisson, and our negative binomial, because they all have a relationship in that they're modeling success probabilities given some n or numbers of failure. And again, the binomial has variance less than mean, the Poisson has variance equal to mean, and the negative binomial has variance greater than mean. And of course, we can also draw arrows to show the relationships between the variables, which random variables are actually special cases of other random variables. And we've barely talked about it, but of course the geometric probability distribution, which is just the probability of seeing k successes before 1 failure, is obviously just a special case of the binomial, or the negative binomial, which is the probability of seeing k successes before r failures. So here we have our discrete random variables. It's a pretty good collection of them. Like with this, we're going to be able to easily make our derivations for our continuous random variables, and we're going to be able to model a lot of interesting phenomena. For example, our rain data and our virology data that we have shared in the class folder. We just want to make one final aside. Sorry that this is it. And it's going to be concerning those random variables in our triangle, right? So our binomial, our Poisson, and our negative binomial. So our final little idea is again about the cousins of these 3 guys, right? And so one mistake we don't want to make is we want to use the random variable to model our data that sort of has the least degrees of freedom, right? So the most parsimonious model we can, that's usually going to do a better job allowing us to make predictions about data. So if we have data that's Poisson distributed, it means there's only one parameter, lambda. We don't want to use a negative binomial which has 2 parameters and overfit our data. Sometimes we do that when we have something called zero inflated data. So I think the most classic example here is, you go outside at work and you talk to everybody at lunchtime, you ask everybody how many cigarettes they smoked that day. And you're going to get a distribution like what you see here, right? So you see a mean of around 5, ignoring the zeros, a mean of around 5, some numbers between 4 and 6. So imagine you have a nice Poisson distribution, but then you have all these pesky zeros. And that's because all the non-smokers always return 0. So you could say, well, if you actually look at that data and try and use the Poisson to model it, you're going to say, hey, this data has too much variance. the Poisson distribution is not an accurate representation of my data, because in the Poisson distribution, mean and variance have to be equal. And of course, the mean of this data is going to be pretty small. It's going to be pulled down by all those zeros, and the variance is going to be greater. So you might be tempted to say, okay, I'm going to either use the negative binomial, or I'm going to use the generalized Poisson, so I can sort of fix my variance to be a greater value. That might be a mistake, because you may have zero inflated Poisson data. You may actually have a nice Poisson distribution that describes the smokers, and then you have a bunch of people who don't smoke. So what would be better to do there, what would be a more parsimonious model, would be to use a zero inflated Poisson. So it sounds complex, but zero inflation is really simple. Instead of a Poisson random variable, you have a two-part random variable, right? So we know how to calculate the probability that k equals 3 given some lambda for a Poisson. We just plug it into the probability distribution function, and voila. Almost the same here. We want to know the probability that k equals 3. First, you have to say the probability that it's not 0. So that's the zero inflation probability, right? So 30% of the time, it's 0. And then the other times, it's Poisson. So you have to multiply that by, say, 70% or 30%. Whatever your zero inflation parameter is, 1 minus that times the Poisson, that's your probability of that observation. Now, what's important is you can still have an observation of 0 that can come from your Poisson distribution or your zero inflation. So obviously what this will do is when you calculate the probability of 0, it'll boost it by a lot, right? It'll boost it by that zero inflation, right? Now we've just added one more stepwise condition. You're less likely to overfit your data if you first test if it's zero inflated and then use a zero inflated distribution when appropriate. So finally, we do have our set of data, but we just want to make an aside that especially for 3 of these random variables, they have very, very useful zero inflated cousins. So to recap, we finished our discrete random variables. So at this point in time, it's going to be in the homework, but everybody can choose a favorite discrete random variable, and we can all sort of become an expert on that random variable. So mine already is, of course, the non-random random variable, so you can choose any random variable except for that one. So the homework's online. Those are the discrete random variables. We've finished that. Next time we do a lecture, we're going to possibly recap some of the tools that we've created to model discrete random variables, but we won't be introducing any more. But we will soon be exploring the space of continuous random variables, which, because we've already become experts across the discrete space, will be easy. So I will talk to you guys next time.